Okay, so let's continue with this. So last time, listen up, listen up, listen up, listen up. So last time we talked about how we have this relationship between the buoyant force and the weight. And if the weight is bigger, you sink, and if the weight is less, you float. You go to the surface, and then you do what you do there. We'll get to that in a minute. And if your weight is equal to your buoyant force, you kind of stay roughly where you are. That's for submerged objects. And so let's do a quick thing on this. So a 5 cubic meter block of material has a density. So here's my block of material, and it's got an area, A, is equal to 5 meters cubed, and the density is equal to 7 kilograms per meter cubed. And that's the object, so let's be careful we talk about and that's a volume, that's not an area, that's a volume. That's a volume of my object, and that's a density of my object. And it says it's placed under the surface. So here's my fluid. And the fluid, so density of my fluid is equal to 9 kilograms per cubic meter. And then what will the object do? Well, let's have a look. My F buoyancy is equal to the density of the fluid times G times the volume of the displaced fluid. And Fg is equal to the density of the object times G times the volume of the object. And I know that these two volumes are the same. V, dense displaced fluid, is equal to V of the object because submerged. It's completely under the water. Oh, so if that is the same as that, and that is the same as that, then I'm simply comparing my two densities. Comparing the forces is like comparing the densities. And so I can say, oh, I can say the ratio of F buoy over Fg is like the density of the fluid over the density of the object, which equals 9 over 5, which equals 1.8. So there's my ratio. What that means is that my buoyant force is greater than my weight. Can you see that? If the buoyant force is 1.8 times bigger than the weight, which is what that 1.8 means, then the buoyant force is bigger than the weight. If the buoyant force is bigger than my, what will it do? Will it accelerate towards the surface? Will it sit on the statically in its location, or will it accelerate towards the floor? Yeah, accelerates up. Yeah, because the buoyant force is bigger. 1.8 times the weight gives you the buoyant force. It's almost 2 times as much buoyant force as it is for the weight. So that should be, that should be like that. Nowhere near as big as that buoyant force. Cool? Now, frankly, you could write down, if you liked, density of fluid is bigger than density of objects, so it goes to the surface. Because you realize, it depends on the densities. You'll find in the book people like to talk about the apparent weight. Okay, so what is this? So we take an object like a bowling ball, and we have a little Newton meter, Newton gauge, and we see what its weight is in air. And then we jack up the water so that it surrounds the bowling ball, and we find that we get a lower value for the weight because there's a buoyant force. So the way we do this is we say, okay, we have the Fg, that's the weight, and then we have our tension, which equals the force apparent weight, yeah? The apparent weight is what it seems to read when you got it surrounded by fluid, and that is the same as the tension, yeah? Thinking back about our connected masses. So we have the tension force, which is the same as our apparent weight. And then we have F, BU, or Y, our buoyant force, which is because we're surrounded by fluid. So I say, oh, the sum of the forces vertically equals 0. So plus F apparent weight added to F B or Y added to minus Fg is equal to 0. I want this Fa apparent weight, and that equals Fg minus Fbu or Y. So F apparent weight is equal to the density of the object times G times the volume of the object minus the density of the fluid times G times the volume of the displaced fluid. So F apparent weight is equal to, didn't take my numbers out, but let's do it now. There's my volume of the sphere, so that's going to be 3. And because it's completely submerged, that's going to be 3. There's no problem there. And then we have the density of the object, so that's going to be 12. And the density of the fluid is 8. And of course G is 10. G is 10. So F apparent weight is equal to 360 minus 3 eighths of 24, 240, which equals 120 newtons. And that's what it said, prove this. And so it proved it. Can you see? I recognized it was an equilibrium, and I wrote down the sum of the forces vertically equals 0. That was from Newton's laws. I then looked at my diagram. I recognized that that little gauge is pulling up, and that's the apparent weight. I suppose I got that from my connected masses. I then looked at my diagram, and I just summed them. So I said, oh, apparent weight force plus buoyant force plus the weight, but that's negative pointing downwards, equals 0. And then just let the other stuff take care of itself. So for me, that's not a whole new problem. That's a little bit. That's me applying my newfound, force is equal to the density times G times the volume. Applying that to this particular Newton's second law problem, really. It's really a Newton's second law problem. I'm just adding in, how do I find these forces? Oh, rho G8, or rho GV. It's rho GV. So it's not a brand new problem. Okay. What about floating? It sounds horrendous, and they tend to make the problems look horrendous, but they're not. When you're floating, the volume of the displaced fluid is not the same as the volume of the object, because there's some of it stuck above. But the forces are the same, because you're not accelerating. So now we know our two forces are the same. F BU or Y is equal to FG. You know I'm a bad speller. You can see it in lab, I can't spell. And for years, I would say BOUY, and then I got to a stage where I thought, that's not right. So I started saying FBUOY or F B-O-U-Y, and it was like confusing. And then after many years of confusion, I realized that my name is spelled B-U-O-N-A-Q. So there was no need to be confused all along. I could have just said it's the same as your name, you know. And I never thought about that comparison. It never occurred to me that my name began the same way. So life is weird sometimes. Yeah, I'm spelling my last name out. Yeah. So when an object is floating on a fluid or at the surface of a fluid, the forces on the object are a buoyant force and the weight of the object. For a floating object, the volume of the displaced fluid must be less than the volume of the object. You can't displace more volume than you have, but you can displace less. But the buoyant force must be equal in weight of the object. So here's an example. A sphere of 2, so here's my sphere, and my density of my object is equal to 2 kilograms per meter cubed. Floats on a liquid, I'm going to show it like that has a density. Density fluid is equal to 8 kilograms per meter cubed. So it's sure that 75% of the volume is above the water. Man, okay. I want percentage above. It sounds awful, but it's not so bad actually when you think about it. What you say is, you say, oh, hold on. F. Start with what you know and have faith that it'll work out. So I know for this kind of problem, F is equal to Fg. Okay, I know that. And I know this is the density of the fluid times G times the volume of the displaced fluid, which equals the density of the object times G times the volume of the object. The object is the object. It doesn't matter if it's in the water or out the water. The weight is going to be affected by it. We're separating out the weight bit from the buoyant force bit. And the weight bit just depends upon the volume, the density, and gravity. So, oh, that's interesting, because you know what I've just realized is the volume of the displaced fluid over the volume of the object. So that's going to be that. Volume displaced fluid over the volume of the object is equal to rho fluid times G over rho object times G. Well, those G's cancel, so it's rho fluid over rho object. Well, that equals 8 over 2. I got that wrong way around, I think. Fluid over the object. Just bear with me a second. Fluid over the object. Yes, I got that backwards. Take that to the other side and it goes on the bottom. It was going so well as well. So take that there, and you've got to take that there. So it's going to be the density of the object over the density of the fluid, not the other way around. Density of the object over the density of the fluid, which equals 2 over 8. Oh! So the percentage of the object below the surface is equal to 0.25 times 100, which equals 25%. So the percentage of object above
must equal 75%. And that's what you've been asked to prove. Now, can you see, we've done no notes to prepare us for this, apart from that force equals that force. And I don't think anybody can see their way through this the first time. But what they do is, they have faith. They say, the only thing I know is the buoyant force equals the weight, so let's write that down. And then they go, oh, this has density and it has volume. And I want to do the ratio of volumes. So let's just get the ratio of volumes and see what I get. Oh, that's the percentage of what's underneath, and I want what's above. Oh, it's just 100 minus that. So can you see how you don't recognize, I don't think most people recognize the end of that problem when they start it. But they have faith in, it's the only thing I know, so I'm going to put it down, I'm going to look at it, I'm going to think, this must be doable by somebody like me, and they do it. That was on my final when I was a student. They had this, we did 4 subjects per test. So literally, we had general physics would be 2 questions after 2 years. And there'd be another thing which would be nuclear physics would be 2 questions. And we did that maybe a year ago. And then on that same test, I might have electronics, which I did last semester. And just all put together. And you've got to answer 6 questions. You've got to answer actually 4 questions, I think it is. So you just pick and you just do it. And they'd made a mistake. Let's hold on here.